Okay, good morning, ladies and gentlemen. I'm Baosong from Alibaba Qwen team. It's my honor to stand before you to introduce, to give this talk. And the presentation topic is about multilingualism of Qwen from foundation model to applications. So the presentation I will divide it into three parts. Firstly, I will introduce Qwen 3, which is just which was released just last week, and I will introduce the multilingualism of Qwen, which we think it is very important capability of large language model. And thirdly, I will talk about some multilingual techniques for applications. So firstly, I think that Qwen recently it has been one of the most popular open source large language models. We have released over 200 models with 300 million downloads, and over 100,000 models was built up on Qwen. And in this time, for Qwen 3, we released 8 sites. Two of them are MOE architecture, and the others are dense models. So we believe there must one that maybe right for your application or your research. So the open sourcing of Qwen is we think it will significantly advance our large language model community. Considering the performance, the flagship model Qwen 3.235b, it achieves competitive results to those SOTA models on popular benchmarks, especially for coding, math, and general capabilities. And we also make a lot of efforts on small size models. For example, Qwen 3.4b uses comparable performance to that of Qwen 2.5 72b. And I think such kind of model can be used for like edge devices. Yes. There are 3 key features in Qwen 3. The first one is hybrid thinking model. We integrate thinking model and the non-thinking model into one model. So it allows us to control how much thinking the model performs based on your tasks. Like the figure shows that when we give more thinking budgets, the performance can be further improved. The thinking model is the default model, and you can query to the large language model, and it will reason step by step before giving your final answer. And this is ideal for complex problems. Then when you are require deep thoughts. And the no-think model, which is as your chat model, you can activate with very easy way to just type no-think at the end of your prompt. So this model provides a quick, near instant response, and it is suitable for simpler questions where speed is more important in your application or your research. And the second key feature is agent capability. This time we optimize coding, agent capabilities, and we strengthen the support of MCP. Yes. Okay. The third key feature is multilingual support, and which is a core topic today. And now Qwen 3 model are supporting over 100 languages and dialects. This figure shows the development of Qwen's multilingualism. For Qwen 1, we only support English and Chinese. But now we can support 120 languages. So let's talking about some details about Qwen 3. For pre-training, this time we use almost use over 30 trillion tokens, and the overall performance of Qwen 3 base model can match that of Qwen 2.5 base model with more parameters. We divided our pre-training process into three stages. First stage, considering the computational efficiency, our models were pre-trained on 30 training tokens with a context length of 4,000 tokens. For the second stage, we further improved our datasets by increasing the proportion of knowledge-intensive data, such as STEAM coding and reasoning tasks. For the last stage, we extend our window size. We use high-quality long context data to extend the context length to 32,000 tokens. Recently, post-training has become more and more important to achieve the hybrid model capability of reasoning and the rapid response. We introduce multiple stage post-training strategy. For the first stage, we used diverse long chain of thought data, which covers various tasks and domains. For example, math, coding, logic, reasoning, and STEAM problems. It's just like how to say it? Code starring, yes. And the second stage, we employ reinforcement learning. This stage focuses on scaling up computation resource for reinforcement learning, and we utilize rule-based reward models to enhance the model's exploration capabilities. And for the third stage, the no-thinking model is integrated into the thinking model by fine-tuning our model with the combination data of long chain of thought data and the commonly used chat instruct tuning data. And the final stage is used for strengthening the model's general capability and correct and desired behaviors. For example, code switching. Yes, and this stage applies reinforcement learning across more than 20 general domain tasks. Another technique we used in Qwen 3 is the distillation. For the largest two models, we training them from scratch, while the small size models are distilled from the two larger ones. Okay, and I would like to thanks to the support of our partners, our friends, and our open source communities. And we believe that Qwen is nothing without your helps. And we also welcome more people, more organizations to join us community, make Qwen become better. Okay, now let's start in the second part, the multilingualism of Qwen. At the beginning of our project, the multilingual is one of the most important capability we should to attend. So from 2 years ago, we starting to explore the multilingual problem of Qwen. This page shows the we examine our Qwen 3 on several multilingual benchmarks, for example, reasoning, knowledge, math, instruct following, and for both thinking or no thinking models, I think the Qwen 3 can yield competitive or even better results than their SOTA counterparts. This figure shows the small size model, and yes, it's surprisingly that we found due to the distillation technique, the small size model can also achieve strong reasoning capabilities, like the blue lines shown. And we think such kind of model is very easier to be deployed on edge devices. We divide different languages into language families and examine our model on Bailey, which is language reading comprehension tasks. And we show that Qwen 3 can yield significantly improvements than Qwen 2.5, and it reduces the gap between a performance gap between the SOTA multilingual models, for example, GMA 3. When we're talking about multilingual, the data is the first challenging, and some researchers argue that we don't need too much data for multilingual because a lot of capability can be easier to be transferred from English or from Chinese to other languages. So to confirm this, we conduct an experiment on Japanese. We continue to train Qwen with Japanese, and we found that indeed some capabilities, for example, math or understanding, are very easier to be transferred. However, there also exists many capabilities such as generation, local knowledge translation, such as they are related to the two data sets. So the scaling is still effective in multilingual. And the data is unbalanced. When we after we filtering the data, we found that from the common crew, only 1% languages have more than 100 billion tokens. Besides, the vast majority of data is poor quality. Most of the data are deduction or has low quality, should be to filtering, and the usable data has a very low ratio. And there exists significant differences in the domain distribution across different languages. For example, in some languages, e-commerce or entertainment are plays a very high ratio. Another key feature we attend attention to is knowledge density. High knowledge density is very important for improving the model training efficiency. We label our data with the educational score, which is also used in the project of FMAP, and we found that a lot of similar, very high ratio of data has low knowledge density. So considering the data, I think there's no much innovations, but just relies on careful data engineering. For example, data selection, cleaning, and balancing. And we also conduct experiments and researches on these topics. When we have data, the next problem is to training. However, there exists a lot of hyperparameters, for example, data ratio, batch size, learning rate. And the figure shows an experiment on Japanese-English data ratio. When we increase the Japanese ratio, and you can see that the Japanese performance is increased, and however, the English performance is destroyed. So it is very important to select a better group of hyperparameters. So we take a lot of efforts on explore the predictable training, and we conduct massive preliminary experiments. And finally, we summarize a formulation that to measure the relationship between performance and the learning rate L and the data ratio R. So in this figure, the solid points are prediction results, and the cycle points are the real results. So they are very similar, very similar, right? So in this way, we can select optimal set of parameters that can be used to balance the loss for English or Chinese and the benefits for other languages. Another challenge in multilingual community is the lack of multilingual benchmarks. So to alleviate this, we release some benchmarks. For example, PMMUO. This benchmark covers 10 languages, 7 kinds of capabilities, and most importantly, all the examples in these benchmarks are parallel. So it can be used to assess the transfer capabilities. For example, we can see that the transfer effects differ for different capabilities. For example, mathematics or coding are relatively easier to be transferred. However, for language understanding, it is relatively hard. And we also found that the scale the model size can enhance the capability transfer for most of languages. For example, Qwen, Jima, or Mistral. However, this phenomenon not exist in Llama. Maybe they use some different data or training strategies. Another benchmark is multilingual mathematical reasoning benchmark. So we released Polymath, and it contains over 20 languages, and we divide the benchmark into different difficulty levels, from low, medium to high and top. And this figure shows some SOTA models some SOTA models. And we can see that recently the open source models, for example, DeepSeek or Qwen QWQ, has used comparable or even better results than the other SOTA closed source models. Another interesting phenomenon is that we found that almost all the models, large language models, especially for thinking models, the long reasoning models struggle to think in multiple languages. For example, when we query for example, Japanese prompt to the model, then it always cannot thinking in Japanese. It's thinking in English or thinking in Chinese. So we found almost all the existing thinking models has this problem. Maybe it's due to the poor capabilities on generation and reasoning in low resource languages. But I think it should be a research topic in future. Okay, now let's talking about some application technicals. There are a lot of applications of multilingual language model. For example, role playing in different culture or different languages, and personal assistant, and oral practice partner, and like efficiency tools for study and working, and as well as cross-border e-commerce. So when we want to build an application, the first problem, the first technical path is to continue pre-training your language model using, for example, your domain data or the data you want to enhance. However, the problem is when you use a high ratio for the new data, it will cause a catastrophic forgetting problem. If you use a low ratio, it will raise the computation cost. Here I give one example. If you have 10 billion tokens for the language, 10 billion tokens for new data, and you use 20% as the ratio of continual training, it actually requires 40 billion tokens replay data. So it's very expensive and not efficiency, I think. So in our community, there are a lot of methods to tackle or alleviate this problem. So here I introduce a method to a method based on a mixture of experts. So we extend the model with the experts to store multilingual knowledge and phrase the original parameters to alleviate the catastrophic forgetting problem. This is a more detailed solution. So firstly, we retain the original parameters to prevent the catastrophic forgetting, like the blue ones. And then we enhance the multilingual capabilities through experts, like the yellow ones. And all these extended experts are initialized with the original FFN layers to inherit existing knowledge. So it is a very easy way to extend parameters to enhance multilingual performance. When we examine our architecture, it can increase the ratio to 50%. And almost no loss in conventional performance, and the multilingual performance is significantly improved. Most importantly, we training the model only requires 40% of original training tokens, and it can achieve comparable results. Another problem is post-training. It still face the overfitting and catastrophic forgetting problem. So especially when you are lacking of high quality data or across different tasks and domains. So here I take an example on machine translation. So to alleviate these problems, we enable the model to understand the input sentence and generate corresponding domain or their thinking path to activate the model's domain knowledge, thereby reducing the or alleviating the overfitting problem. So you can see that the chain of thought fine-tuning strategy can efficiently elevate the overfitting and shows more significantly improvements on out-of-domain problems. So I think this is also same to the COT fine-tuning strategy in recently reasoning models, the pre-training process of recently reasoning models. Another problem is cross-lingual cross-modal. One of the typical application is speech translation. The conventional technical path is a cascaded architecture, which chains automatic speech recognition model and punctuation model and machine translation model. It's very complex, and there exists error propagation and has high latency. So the large language model gave us a new solution to tackle the speech translation problem, that is end-to-end speech translation. So here we align the audio and the text. The large language model we use here is a multilingual version of Qwen, which is continually training use multilingual text. And the audio encoder is a sense voice, which is also a multilingual speech foundation model and released by Alibaba. And there is a projection layer is inserted between encoder and large language model to align the two different modules. And we found that the end-to-end model can use significantly improved than the cascaded ones across different domains and different languages. Another superiority of large language model is generalization. We can fine-tune it or enhance it with field data, field samples, to achieve some new, to learn some new capabilities. For example, waiting for long dependency reordering, or predict the next token according to context rather than only according to the source sentence. So in this way, the end-to-end model can, the latency of end-to-end model only 0.5 seconds. As a comparison, the human experts require 3 to 5 seconds. Due to the limitation of the presentation, I cannot talking more about these details. So you can read our papers, or by the way, the technical report of Qwen 3 may be released this night or this afternoon. So you can read these papers, and here I would like to share some potential research directions in multilingualism of RMs. For the multilingual pre-training, the fundamental principles and efficient training and interlingual between among different languages, and the capability extension, for example, how to lightly extend a new language, and or enhance an existing language. And most importantly, the data engineering, how to collect, filtering, or generate new data. Considering the post-training and applications, we can explore the supervised fine-tuning and reinforcement learning. For example, which capabilities can be transferred from the high-resource languages, and which cannot. By the way, there exists mitigating biases in language models regarding to different languages between different cultures and habits. And similar to this presentation, the evaluation is still a research topic in this community, and we should to take more attention to knowledge enhancement. For example, we found that RMs tend to believe the reference from high resource languages rather than the low resource ones. And we can explore the knowledge boundaries of low resource languages. At the end, the multimodal agent and applications can be further explored. Okay, that's all. Thank you very much.